I want to call this speed run physics. Speed run Lagrangian, but it's not because it's going to take some time. But I'm going to rebuild this. So I'm going to do Lagrangian mechanics problems, and I'm going to animate them textbook quality. So here's the one first I'm going to make. I'm going to remake this for you. Let's run this. I'll put a time delay on there so you can see. So this is a mass connected to a spring, and then on the other side, that's a mass hanging over a pendulum. And that looks nice. Look at that. Look at that. That's just cool. We're going to make this. We're going to solve it and make it. Solve and make. So let's start on the board to solve this. Okay, so we do need a little bit of work here. We can't just do everything. I'm going to use SymPy, Python with Jupyter Notebooks, and VPython together. Not together, separate. Okay. So the first thing we want to think about is how many degrees of freedom do we have in this situation? And the answer is just one, right? Because if this moves that way, that's going to move down that way. So I need to pick my generalized coordinate. I'm going to pick this as x1, and I'm going to call this y. Actually, this is the value. I'm going to have negative y2. So I do have two things, but one variable. Because those two are connected, let's call the length of the string r, such that y2 is x1 minus r, right? And that will make this a negative value. I do want that to be a negative value. So x1 plus, well, it's not quite true, but x1 goes that way. Actually, no. I think that works. So let's say if this moves, okay, let's call it, okay, this makes more sense if I put it like that. So x1 minus y2 equals r. So y2 equals x1. Okay, I had it right. Okay, good. Now I want to find the Lagrangian, which is pretty easy, right? Because I can write the kinetic energy as 1/2 m1 x1 dot squared plus 1/2 m2 y2 dot squared. But I don't even need to write that out because I'm gonna do that all in just a second. And then u as mgy2, right? That one does plus 1/2 k x1 squared. And then the Lagrangian is just, I'll just write this as t minus u, don't really care. 1 degree of freedom means one Euler-Lagrange equation. The partial of L with respect to x1 minus the time derivative of the partial of L with respect to x1 dot equals 0. That's what we're going to do. I'm not going to do any of the math. And this is an easy problem, okay? But I want to do this with SymPy because, why is my fan on my computer? I don't know. I want to do this in SymPy because it's going to help when we get to more complicated two-dimensional problems. This will make it a little bit easier in that case. So let's jump over to SymPy in Python. I'm going to have to use Jupyter Notebooks here. So that's VPython. I got it right here. Okay. From scratch, let's do it. First thing we need to do is to import the module. Import SymPy as SP. And then I always run that just to make sure that things are functioning. Now I need to declare all my variables because I'm going to make a symbolic solution. I need to say what letters are variables. So I have R, K, T, M1, M2, G. Do I have everything else? I think that's it. And these are of a type sp.symbols. And then here you can give it another name. I'm going to do it both ways. So you could say R, you don't need a space, K, T, M underscore 1, so give make it look nice, M underscore 2, G. Okay, and then you can just do, M1. I'll show you what it looks like. No, you can't. Okay, that's fine. We'll get to that in a second. What does it say? M1 is not defined. Oh, M1, that's right. Okay, so then it does give my little underscore right there. I don't want that because it's going to cause problems in the future. So I'm just going to call this M1 and M2. Is that okay? And you'll see why. Now, in terms of, I do have other variables. I have x1 and y1. I'm going to define those as functions. So x1 is sp.symbols. And again, I'm just going to call this x1 by itself, and it's going to be sp.symbols it's going to be class CLS is sp.function. It's going to be a function of time. I need to define that. And again, I could say x_1, it would make it look nice, but I don't want it to look nice. I just want to get it done. And R means raw. That's what that R right there means. It means the raw string. And I don't think you really need that right there, but I'm missing a parenthesis. And then y2 is the same thing. sp.symbols, spell it, R y2, class is sp.function. Now I need to say what those are functions of. I feel like something's not working right. Unmatch, yeah. Oh, I guess I didn't need that. Okay. So now I need to say what are these functions of. So x1 is a function of time. So x1 equals x1 is a function of time. You can do that because I said it was a function. y2 is y2 as a function of time. And now I need to define the derivatives. So x1 dot is the we use dot notation. So x1 dot is the derivative sp.diff of x1 with respect to time. X1 double dot is sp.diff x1 dot t. And again, this is easy. We don't even need to do all this stuff, but it's good practice. And then y2 dot equals sp.diff. Y2, I don't even need to do that. I'm going to do it anyway. T, and then let's go up here and say, actually, I don't need to say this is a function. I just need to say y2 is x1 minus r, right? And then so x1 is a function of time, so y2 is a function of time. And then I need y2 double dot, I actually don't need that, but diff y2 dot and t. Okay, so now I can define my kinetic energy. T is sp dot diff 1/2. That gives me the fraction, no, not fraction, rational. That gives me the fraction 1/2 times parentheses m1 times x1 dot squared, right? Because I need to take the derivative, the velocity, plus m2 times y2 dot squared. That's the kinetic energy. The potential energy is m2 times g times y2 plus sp dot rational 1/2 times k times x1 squared. That's the spring potential energy. Then L is T minus U. And if you want, let's just go ahead and let's just check. What does it give us an L? Okay, it does. And that seems fine, right? There's my Lagrangian. Now I'm going to define LE as the Euler-Lagrange equation. No, what did I do that for? Sp dot diff L x1 minus sp dot diff L x1 dot t. So that's the derivative of, with respect to time, of the partial with respect to x1 dot. And that gives me the Euler-Lagrange equation, and we can print that if we want to, and that's what it looks like. But now I want to do something just for, I want to solve this for x1 double dot, that term right here. So how would we do that? Let's say solves is sp.solve. I want to solve, let's say I get this notation wrong, the equation SLE with the variables x1 double dot. And then let's just say solves x1 double dot simplify. Parentheses, no parentheses. I can't remember. There we go. And that is the answer. I know the answer is pretty easy. There we go. Now we just need to implement that in Web VPython. So we got a lot of work to do there. Let me just do this real quick, because one of the things that we're going to do in the future is to print this. So it would just be not an equation, but now I have the code, and I can change that code into a differential equation in Web VPython. Okay, now let's jump over to Web VPython. So we do have a lot of work to do over here. Let me just move this out of the way so I can see that. Okay, we're drawing stuff now. So we have to deal with, I'm going to make a box, another box, another box, and a disk, strings, springs. There's got to be a whole bunch of stuff. So now we're starting the art part of this video. And so here we are, we're blank. Okay, so the first thing I'm going to do is to make some variables. And I'm just going to use the same variables I used before. That's why I'm just going to copy these. Because I don't really want to think about it, type it. Okay, oh, that's not the ones I want. I want these. Okay, so that's what I want. Now let's make this bigger so you can see better. That's good. So G is my gravitational constant. R is the length of the string. This should be x1. x1 is the initial position of the thing. I have to give it some initial value, otherwise it won't move. And then I'm using capital M1 and capital M2 as the masses, and K as the spring constant. So that's that. The first thing I'm going to do is to make the mass on the table. I'm going to call it M1, lowercase. I know that's dumb, and there's better ways to do this, but it's fine. So the box is a 3D object in Web VPython, and it is troublesome because the position of the box is the vector in the center of the box, and then the size is, so forth. So if you put the vector, the position at 0, 0, 0, and then you give it size, the sides aren't going to be at 0. But that's fine. We'll just work it out. I find the best thing to do is just to make stuff and then adjust it as you need to be, because it's hard to kind of like pre-calculate out everything. So I'm not going to do that. Let's just say the box is at a position. What did I give it? Let's say vector x1, 0, 0. And then the size, I want to use the same size as before. The size of this is, I'm just going to copy it. And so what I was trying to do is like envision a real cart that I would get from my tracks and stuff like that, and that's what that'd be. Color is color.yellow, and I think that's all I need. Yeah, okay. And did I have a closed parenthesis? Nope. Okay, and then I always like to run it. Every time I make an object, I run it. And there's my box. Yay. Okay. Now I need another box for the track, right? So the track is also going to be a box. And it's going to be positioned lower than that so the box can be on top of that. And so I have a box with a height of 0.02. And so my track is going to be below that. I'm going to just use the same values I had before. I'm going to copy these because it took a while to make them, and then to play around with it. But seriously, just make the box, and then you kind of have to like run it and see if it looks good. So see, that looks good. And if your box extends into your track, well then just move your track down, or just say don't worry, it doesn't matter, right? It doesn't really matter. Now I'm going to need a wall, right? Because I'm going to have that spring connected to the box. So let's call that a wall, and it's a box. I'm going to do this one live. So my track has a size of 0.2 meters, and it's at the x value of 0. So that means if I go over to negative 0.1, that's where I want my wall to be. So the position a little bit more than that. Let's just start with a vector of negative 0.1. And then the height is going to be equal to, let's say, my height of my box is 0.2. I want it somewhere around there. Let's say 0.2. And then the z value, which is in and out of the thing, is 0. Now for the size, I want, see, this is going to have to be a little bit bigger. Put the size of vector 0. Not 0, 1. Is that 0, 1? Yeah. So I multiply that by 2. I think that's not going to work. Okay. And then the height, let's say 0.04. And then I think this should be 0. Yeah. And then the width is going to be the same as width as the track, which is 0.05. And I left it as just gray. So let's just run that and see what it looks like. Okay, that's wrong. You see why you run this? Okay, my height, my wall, 0.2, 0.02 it should be. Yeah, Okay, really close, you see. Now, let's just move that down a little bit, 0.15. This is where you kind of play around with it just to get it to work. I'm going to move it down even more. That's 0.1. Good. That's pretty good. Okay, now for the spring. So the spring has an attachment point. You can think of it as a point in space, right? Where I have to connect it from one point to another. And I use the two important values for the spring are the position, which is the location of one end, and then the axis, which is a vector to the other end. And I want it to be in the x-axis, x direction. So what did I do before? I did P, I went from there. So I did make a point. Okay, so let's make a point in space. I'm going to make a point in the wall, or somewhere near there. I'm going to call it just P1. It's my marker. It's going to be vector. It's going to have the x value of the wall, so negative, let's say negative 0.1. It doesn't really matter. And then the y value of the box, so 0.02, and then z value of 0. So that's one thing I can use for my spring. So now my spring 1, let's just only have one spring, is of a type, is it a helix? Yeah, it's a helix. Helix, position is P1. Now the axis, I want it to go from P1 to the box. Now that's going to go to the center of the box, but I think it's okay to do it that way. So axis is going to be equal to m1.pos minus p1.p, not just p1, just a vector. Now I need the radius. The radius is, let's say, 0.01, and let's just leave it like that and just to see if it runs. Okay, so that did not work. My P1 is negative. It should have the same vertical position. Oh, 0. That's why. There we go. Now the radius is too big. Let's fix that. So the radius is 0.02. Let's try that. Okay, now I want it thicker. So let's make the thickness 0.002. I can't remember how they define thickness, but that looks good. I just guessed. Now I do want one more thing, and that's a property of it called, I think it's called coils. Yep. So coils tells you how many loops there are. The default is 5. Let's say coils equals 15 and run it. Now that looks like a spring. I might want to make it a little bit thicker, the radius a little bit higher, let's say 0.4. This is the art part, right? There you go. Check that out. Yes. Okay, now I need to make the pulley. And this is going to be a little tough, right? Because I need to make a disc right here. Let's just go for it. Pulley is it's actually going to be a cylinder. So the position of the cylinder, do I need to get, I do, it's going to be shifted off a little bit because I want it to have some thickness. So let's give it a position in the negative z direction, but vector on the other end of the track, so the track has a size of 0.2, so it's going to be 0.105, I'm going to guess. The y component is going to be 0, right? So I want it, no, I want the top of that lined up with the, so let's say R pulley. Let's make a radius of the pulley. RP. It's going to be 0.0, let's see, the spring had a thickness of 0.02, so 0.005. Maybe try that. So in the y direction, I want to shift this down. So it's going to be negative RP. And then in the z direction, let's just say negative 0.001. And then the axis is going to be vector 0, 0, 0.002. Let's just try that. Nope, I didn't give it a radius. Radius equals RP. Okay, that looks pretty good, right? I want it a little bit bigger though. So let's make the, yeah, I want it a little bit bigger. So let's say the radius RP is 7. I'm just picking a value here. Okay, so now it's on the table a little bit. I mean, I guess it's okay. Let's just increase the x value a little bit. So 7. Okay, I think that's good. That's good enough. Now I'm going to make a string. Okay, this string is going to be pretty easy. String 1, I need 2 strings. String 1 is a cylinder. Position is mass1.pos. And then the axis is going to be that point on the pulley. So it's going to be equal to axis is going to be that point on the pulley, on the top of the pulley, is going to be pulley.pos plus vector 0 rp0, and then minus m1.pos. And the radius is going to be equal to 0.001, and let's just see if that works. Okay. Pretty good, pretty good. Now I need to make the second mass. We'll call that M2. So I need to go ahead and calculate my value of y, which I'll call y2. y2 is going to be, what did I say before? x1 minus r. So M2 is a box. You could make it as a sphere if you wanted to. Position is going to be vector, the same as the pulleys, the string. No, the end of the pulley. So it's going to be pulley.pos plus vector rp00, right? Because I need to shift it over some amount before I go straight down. And that's going to, and then minus the vector 0, no, plus the vector. And see how complicated this gets? But we only have to do it once so we can use it again. 0, y2, 0. Okay, so that's the position. Now the size, let's say it's, this one is 0.7 by 0.02. Let's just make this vector 0.02, 0.02, 0.02, and then let's give it a color. Color equals color.cyan. And you notice how, like, every time I make something, I run it. It's not there. Okay, I made an error, that's fine. Okay, we're down here, mass to position, that's fine, 3. Size is vector, that's 3. Wait, then what's the problem here? Box is position, pulley.pos plus vector. Well, let's see. Is it the color? Color equals color.cyan. That's right. Let's just comment this out and see if it gives me an error. That's how we find out where the error is. No error. Okay. So, box position is vector pulley.pos plus, oh, yeah, that's right. RP is that. 0, y2. Let's just take this out and see what happens. Although I think it's on the size. 0. Three arguments. Okay, so it wasn't that one. You probably see the error and you're like, dude, it's right there. And I'm like, well, I don't know anything. Okay, oh, I see why. I see why. I said vector. And then this was plus vector 0, y2, 0. See, I figured it out. Sometimes you just takes a little time. Ah, I messed up again. Too many parentheses. Okay, box, pulley, vector. Position equals pulley. Oh, okay. Got it. Okay, now I need to make string 2. And I know this is just all the art, but once we get all these things set up, we can animate it pretty easily. String 2, I'm going to go from the box up. So it's going to be position is going to be equal to m2.pos. Oh, I didn't see what it was. It's a cylinder. Position is that. And then the axis is going to be that point on the pulley. So it's pulley.pos plus vector rp00 minus m2.pos. And then I'm going to have the radius is the same as the other string, which was what? RP. No. String 2, 0.01. 0001. Okay, look at that. Now, I do want to be able to see the string, and then you'll notice there's a little problem that it's not a huge deal, but we want it to be perfect. You see how there's no string from there to there? I'm gonna add that in, and I'm gonna use a little trick, because I want it to be nice. So, but to do that, I'm gonna first change, so you can really see it, I'm gonna change the color of the pulley to darker gray. So it's gonna be vector 0.5, 0.5, 0.5. So you can write vector as a color, and that's RGB colors. Oh, now it's all gone. Object X is not supported. Wait, all I did was, it was working. Oh, maybe the string didn't work. No, it did. Oh, color equals. Okay, there you go. Now I just want to fill in this part right here. So what I'm going to do is to make a temporary value, and I'm going to put just spheres on that part of the outside of the pulley. So let's make a variable. I'm going to call it alpha equals vector 0, and then d alpha is 0.01. And so I'm going to think about moving along that circle just like that. While alpha is less than pi over 2. All right, so I'm going to go from here to there. And so what's the vector value of that going to be? I'm just going to move along that axis. So I can say rtemp, let's call it rtemp, is just going to be equal to pulley.pos. That's where I'm going to start. And then I want to add in rp times vector cosine alpha sine alpha 0. Oh, comma. And then I'm going to put a sphere there. I'm not even going to give it a name. The position is going to be equal to rtemp. And the radius is the same length radius as the string, which is 0.001. And then increase my value of alpha. So alpha equals alpha plus d alpha. Okay, let's see if that works. Look at that. I mean, so those are really just a bunch of little spheres, but they're right on top of each other. It looks like a curve. And I don't need to move that, right? Because as the string goes up and down, I'm going to change the length of string 1 and string 2, but that part on the curve is going to stay the same. Okay, we are ready to rock and roll and animate everything. Oops, oh my gosh, did I just delete the whole thing? I did. Are you kidding me? Okay, this is where in those, let's see if I go forward. Okay, fortunately I did save it, so I'm back. And hopefully I edit these things together, which I sometimes have had problems with, but okay. So now we're ready to start calculating the real meat of the stuff. I do need to include my initial conditions, so I need t equals 0, dt is 0.01. I need my x1 equals, I got that already, x1 dot equals 0. That's all I need, right? Yeah, so while t is less than, let's say 5, let's run it for 5 seconds, rate 100. Number 1 is to calculate x1 double dot. Now, we have that, right? It's over here. There's x1 double dot. I'm going to go ahead and just copy that. That's my x1 double dot. I'm going to go back over here and paste it. So x1 double dot equals that. Now, it's wrong. right? Because it has x1 as a function of t. So I'm just going to delete that part right there, put my parentheses back in there, and then everything's fine. Everything's fine the way it is. So I can leave it like that. Now that I know x1 dot, I can update x1. x1 equals x1 dot equals x1 dot plus x1 double dot times dt. Now I can update x1. x1 equals x1 plus x1 dot times dt. But now I have to do the work of moving all my stuff, right? So I need to move mass 1. So let's move mass 1. Mass 1 dot pos equals vector x1, 0, 0. That's pretty easy. Now let's move mass 2. Mass 2 dot pos, let's calculate y2. y2 is x1 minus r. So m2 dot pos is vector 0. No, it's not. I could just move the value right there, but let's just copy this whole thing right there. So it's just this whole thing right there. And it has a new value of y. So now I've moved both those masses. And let's update time. And before we go into moving the strings and the spring and everything, let's just run this. And we should see those two masses going like that. And that will tell us a lot if we're on the right track or not. Let's see, we're not. M1 is not a function. Okay, so I think I have another code error in there. Let's save this. M1 is not a function. Oh, these were okay, M2. I can use capitals. See, this is why we run it. So we can find these errors. Oh, see, that's going backwards. Y2 is x1 minus r. Y2 is x1 minus. Obviously, that's minus. No? Y2 is x1 minus r. So x1 goes that way, y2 gets smaller. So as x1 gets smaller, y2 gets more negative, but it's going backwards. Let's just do this. m2.pos.y equals y2. What did I do before? I had y2 is negative r minus s. So negative r plus, that's y. Negative r plus, the same thing. I must have done it wrong in my differential equation. That must be it. Negative, no? I had this. I had negative r minus x1. Let's just try that. I think it's the same thing, but what the heck? Why is it going backwards? Oh, then down here, let's just say negative s. What am I doing wrong? Negative g m2 plus k x1, m1, m2, that's fine. x1 dot, double dot, x1 dot, m1 dot pos, negative yes, that's right. Okay. Good. Now I can update the strings. And the spring. So now let's get to work there. I'm going to update the spring. Now look at the spring. The spring up here, it had the position at P1. So I don't need to change that. I just need to change this, spring.axis. And let's just run it, see if the spring works. Cool. Now I need to change string 1, which has a math. If I move the position of the string, it's fine. And the same thing for string 2. So string 1.pos equals m1.pos, string 2.pos equals m2.pos. And that should do it. No. I guess I got to change the axis too. Yeah. Okay, so string 1.axis, I just need to recalculate the same thing right there. Now, now that I'm thinking about it, if I would have put the position on the other end, it would have worked better. String 2 axis is this. Copy it. It's the same thing. String 2. Okay. Check that out. It sometimes zooms up, goes faster when you move it. I'm not sure why. But if you want that for a picture or something like that, you can change the length of the string and all that stuff. But I mean, that's picture worthy right there. That's pretty good. Okay. Code down below. And I had some more to do, but it took a lot longer than I thought. I'm not sure. Maybe I'll just show them to you. I'm not even sure. But that's that. I'll talk to you later.